Okay, so in this video we're going to look at the Gaussian integers. The Gaussian integers are um, the following subset of C. So this is a subset of C. And I've forgotten at this point if we've shown it's a subring or not, but it's not too hard to show that this set is a subring as well. We're going to see in a little bit, so in a minute, we'll see that, so I don't know why it's flickering like that. But in a minute, we'll see that subrings of domains are domains. And C is a field, so this guy is a domain because it's a field. And in particular, this set will be a domain. Now, we don't have that theorem yet, so what we're going to do is we are going to do it by hands, namely, we're going to assume already that it's a subring of C, and then show that there cannot be no zero divisors. It's a good skill to be able to, well, do algebra. What's doing algebra? Manipulating symbols. And so there is this theorem that would just get rid of all the work for us, but we need to develop some manipulation skills. So that's the point of this video. Now, how do you show there's no zero divisors? Well, you suppose that you have two elements. Well, hang on, let me just say what we're going to do first. So we're going to show that the Gaussian integers is a domain. So to be a domain, we have to be non-zero. We can't be the zero ring, so it's non-zero. We have to be commutative. Okay, we're a subring of a commutative ring, so therefore we're commutative. And then we have to show that there's no zero divisors. All right, so that's going to be the involved part. So to that end, we're going to suppose that we have two elements in the Gaussian integers, and we multiply them together, and we get 0. And of course, 0 is 0 plus 0i, but we don't usually write that part. Okay, so suppose we have this. What we're going to do now is we're just going to multiply out the left-hand side, and we're going to get a system of equations from this. So the product of a plus bi with c plus di is ac minus bd plus ad plus bci, and that's equal to 0 plus 0i. So that tells us two things. It tells us that AC minus BD is 0, and it tells us that AD plus BC is 0. Because for two Gaussian integers, or in general complex numbers, to be equal, the real and imaginary parts have to be equal. And let me just observe something here. So this system of equations is really the system AC is BD, AD is negative BC. And we're going to go into a cases argument, because what we're trying to deduce is that the only way to have a product being 0 is if one of these a plus bi or c plus di is 0. So what could happen? Well, if a equals 0, then using this first guy, let me label them 1 and 2. So 1 tells us BD is 0. But these are integers. The product of the integers b and d is 0. Z is an integral domain, so this tells us that b is 0 or d is 0, as z is a domain. So we're using that. It's built with a domain to do this. Okay, so 1 tells us this. If b is equal to 0, then a plus bi is 0 plus 0i, and we're done. And so this shows that one of the elements 0, so we're done. Otherwise, d is equal to 0. If d equals 0, then 2 tells us that negative BC is 0, or equivalently, B is 0, or C is 0. Well, if B is 0, we're done. We already said that. So if C is 0, then C plus DI now is the one that's 0. And we're done. Okay, so all of this is saying is that if A is 0, then actually one of these terms has to be 0. Okay, and similarly, if B is 0, you can do a similar analysis, and if C is 0, you can do a similar analysis, and if D is 0, you can do a similar analysis. So what this actually tells us is we can conclude that none of them are 0. So none of these terms here are 0. Great. We're almost done. Let's multiply 1, this first equation up here, this guy. Oh, sorry, where is it? Let's multiply 1 by D, and we're going to multiply 2 by C. So multiply 1 by D, and we're going to get ACD is BD squared. And we're going to multiply 2 by C, and that's going to give us ACD is negative BC squared, if you do the second one by C. Great. Cool. So this tells us then that BD squared is negative BC squared, but B is non-zero. Okay, so let's mark that. Then what are we going to get? We're going to get B times D squared plus C squared is 0 from this equation if we add the from this guy if we add the BC squared over. And B is not 0, so what must be true? Well, since Z is a domain, it must be that C squared plus D squared is 0. But C and D are both non-zero. So what must be the case? Well, we have a contradiction. Okay, so what have we contradicted? We contradicted the fact that none of these are 0. Okay? So it must be that one of them is 0, in which case we have, in fact, that one of the whole terms is 0. All right, so that was kind of a, you have to, when you do these sorts of computations, you normally will break it down into cases based off whether a term is 0 or not, like we just did, and then you try to reason as we did in this example.